Okay, because I'm sick, I'll just go through some of the important aspects of week 7. The recording is available there from the past, so you can watch for detail. But today I'll cover just quickly a few steps, and then we'll solve some of the numerical problems. Is all right? Okay. How far I go, I'm not sure because I'm not feeling that well, but I want to cover a little bit so that it will not be that hard later on to finish up. Okay. Let's go to the screen. Please, guys, keep talking. Yeah, so we'll solve some problems. But before that, I want to go quickly over the lectures. Okay, so there is of course, the theory you can study by yourself. It's not hard, right? Yeah. There are some tutorial problems we will be solving. So swirl reinforcement. Yeah, sometimes we learn about retaining walls and the things. Yeah. So sometimes we need to improve by reinforcing it. Yeah, putting something inside, particularly in the retaining wall. Okay. So it's not general swirl stabilization we are talking here. We are trying to restrain some unsupported slopes or walls so that in the soil becomes more stable. So if this is part of earth retaining structure again, still we continue, but slightly different concept and it's a new concept. So we will in this particular topic, we'll be covering 3 types of reinforced wall. Okay, one is metal strip, using metal strip, another using geotextiles, and then geogrids. We'll do one of the examples for each of them today. Okay, so reinforcement can be a different types. And then we also need to check for internal stability as well as external stability. So reinforce retaining walls. It's not reinforcement to improve the swell at other location, but just reinforcement to improve the wall stability. All right, yeah. So I'm not going to read this. There are a lot of examples, pictures. You can have a look on that. All right, okay. So what is most important thing? You can read that by yourself or view the recording I have already there. So main thing what I want to cover is what the design involves. When somebody says design reinforced wall, earth walls, you need to follow some of the steps. Number 1, you need to find choice of reinforcement. What type of reinforcement you are using? Either is the metal strip or the geotextile or the geogrid. Okay, so only 3 types we cover in this unit. And then calculation of lateral earth pressure. I'm sure you have done that before in Rankin's theory is used, very easy, not the Coulomb's theory here. So very simplified, you know how to calculate lateral earth pressure. Good, right? And then now you need to check for internal stability, that the reinforcement itself, how, what is the spacing, like you see where to put that one in the wall, what are the vertical spacing, yeah, what is the horizontal what they call spacing, if it is like a metal strip are used, if textile we apply throughout the horizontal, right? Yeah, so there will be no gap. Geogrid's also the same. But if there is metal strip with metal tie we are using, in that case you need to find the vertical spacing, how we put that one, and then horizontal spacing. And then how long it should be in the wall. For example, if this is a wall, yeah, this is the wall, yeah. So now is some height there. So now we put, so how long reinforcement we put in, length, right? At different levels, you see, look at the reinforced walls. Yeah, so how long this reinforcement would be. So vertical spacing, we usually call it SB. And there is a horizontal spacing also, if it is metal strip. And then also how long it will be. So you need to calculate length. In the case of geotextile, we don't live like this. We just wrap it around. Okay, we just wrap it. So we call it wrap length, how much we just twist it so that it is more stable. So there's a wrap, we need how long that should be. We use minimum of 1 meter, but there is an equation to calculate how long it requires. If the equation gives less than 1 meter, just use 1 meter. If the equation gives more than 1 meter, you need to use that. It's good, right? And then external stability, same thing, sliding, overturning, and the foundation failure, bearing capacity. We did that before. Okay, so these are the 8 steps we need to check for each case. Okay, there are 3 types of reinforcement we will be talking in this unit: metal strips, geotextiles, and the geogrids. Is it clear? So that's the design approach. Okay. Yes, okay. Let's go straight to these types. Okay, there are a lot of explanations, theory inside, so you can have a look on that. All right. So let's do this one now. Yeah, let's go quickly, briefly about this. I'm gonna move this somewhere down. All right. Okay. So metal strip, right? Yeah. So look at here. How we put that is metal strip reinforcement. So there will be a vertical spacing as be there. I think that is written somewhere. Yeah. Spacing, vertical spacing, and there will be a horizontal spacing also. Yes, because they are just a strip, right? There will be width of tie. How much is the width of tie, as well as thickness T, and then length LE. Not LE, but L, less total length first. Is that right? Yeah. So now, what happens here? I want to put this in the side. Yeah. Okay. Good. So that's how we put. Again, there is a skin cap. They are very flexible. So just to support. We are not designing that, right? We call it cover or skin. So designing metal strip reinforcement retaining wall means you need to find what is the horizontal spacing, what is the vertical spacing, right? And then also how long they need to be and how thick they need to be, thickness, and then width of the tie, W. All right. In many cases, they are default, right? You buy in the manufacturer, in the industry, yeah, they have specific dimensions. Your job now is just in that case is how long it needs to be and what's the spacing. That's it, right? Let's cover those. So again, there are a lot of theories involved. You need to understand is this now, right? Look at here. This is the starting bottom of the foundation. This is the failure line. So before the failure line, we call it LR, length required before the failure line. We can easily calculate from the proportion. And then we call it equivalent length after the failure line, LE. So when I add LR plus LE, it becomes the total length of reinforcement. It depends on the pressure giving, right? Yeah, the pressure giving to that lateral earth pressure. Sometimes there is a surcharge, then it becomes a little difficult. Yeah, but if there is no surcharge, it's very simple earth pressure calculation, right? Even given the surcharge, there are equations to compute. Yeah, this is due to swell only. Yeah, and that's due to surcharge. So we sum them total together. There are equations. All right. Okay. So now I'll not cover this now. Yes, just now. So how much is the tie force now? We need to calculate. Okay. So because you remember there is a vertical spacing of SB, and then horizontal spacing of S heads. Yeah, that's the bulk of soil or tie should support. That support. So that means tie force T must be equal to what? That's the total area and multiply by lateral earth pressure pushing out. All right. So that means sigma A lateral earth pressure due to that block of soil times that's the area. So SB times SH, right? That's the equations there. Again, that is calculated as what? Ka gamma H, right? We already know that, right? Active earth pressure theory there. So that's the one. So we need to win. Sometimes tie can break. So this is the equations we use to check. factor of safety for B is required. All right. Yeah. So we can use this equation whether the tie will break or not. Because pull out, sometimes you see, we put the towel in the wall, tie on the wall, sometimes it just comes out. Why? Because you see, earth pressure is pushing. So that means sometimes you just pull out friction between. You see, tie, can I write the like a shape of the tie? So there is a swell there, swell underneath. Yeah. If not enough friction there and at the bottom and at the top, sometimes it just will share. Okay, so that's the second criteria we need to check. I pull out, and then total length I already mentioned. It should be the failure length plus equivalent length, the extra length, effective length. In this case, you can sum total together using this equation. You see, this is the first one is LR, and the second one is LE. So you can straight use this equation to calculate how long the tie should be, reinforcement. If you see here, it varies with the depth. Yeah, of course, you can feel that, right? This is the wall, this is the failure line, right? Yeah. So that means after the failure, there is a LE, effective length, and before the failure, there's one. So all in different depths, length varies. Instead of doing that, what I would do, I would calculate at the top, how much is that? Yeah. So then use the equations to calculate and apply throughout so that you can get the same length throughout. Otherwise, it would be very difficult to design a small piece different length. Yeah, so the best idea is to get the critical one and apply that length throughout.
So we can take the average or not?
Not average. I think I would go for the maximum. Yeah, so what is the highest value? Of course,
Okay.
close to highest. Anyway,
Yeah.
if you use highest, I know it will be expensive, but it will be more safer.
Yeah.
Good. All right. So length. That's it. And then again, check for overturning. Of course, we know, right? Yeah. So we check here. Over here, we calculate moment. Load will push this side. Pressure would lateral earth pressure will push this side. And you calculate overturning moment and then resisting moment. You know how to check for overturning now. Another is sliding. You see, sliding also same concept. If this is a wall, whether it slides or not depends on what. What is the friction here? The swell and then foundation friction. Yeah, there is a resisting force, and then active PA will push that out wall, right? So ratio between these two is factor of safety against sliding. But usually in foundation, this type of reinforcement, usually the phi of the backfill is reduced by K. So K is 2/3. Make sense? And the third one is bearing capacity is same, but bearing capacity is very easy here. We are not going to use the foundation design, those type of bearing capacity. Will be simple. How much is the pressure there? Okay, so sigma naught, which is what? Gamma H pressure there. And then you try to get the bearing capacity from the foundation, right? Yeah, so use like a Hansen or Wisick equation, and then take the ratio. So we'll get the factor of safety against what? Bearing pressure. Really, that's it. So three, we call it external stability. Okay, let's do one problem now. Come on, guys, be ready. Now let's start. What I do is I wanna just discard this and I put side by side so that I can see these examples, and then I want to minimize this for now. Okay, let's do some problem. You can see my side by side screen, yeah? It's good, yeah? So
Yeah, so we can see it.
all right, okay, look at here. Now let's do example 8.5. Again, I mentioned there will be only 3 types of reinforcement we will be using this week, right? 8.5 example, which is same as tutorial exercise 7.3. All right. So what is that? 10-meter high retaining wall. It's a 10-meter, right? Yeah. Retaining wall with glass strip. That's the metal strip we are using. granular backfill. Backfill is all granular, poisonless soil. So backfill is what? Phi equal to 36-degree angle, right? Yeah. And then density gamma equal to 16.5, yeah, kilonewton per meter cube. And then foundation soil here, phi is 28. Oh, that's also the poisonless soil. C is 50 meter cube, right? Yeah, and the meter square is the C, right? Yeah, meter square, and that's a 17. Gamma is 17.3 kilonewton per meter cube. You see now, the width is given, but no thickness here. You see, did you see width of the strip, the steel strip? So the vertical spacing, horizontal spacing given, and the yield strength given. So there's a friction angle at the bottom here. When you have this, that's given. The factor of safety given. Yeah, easy, right? Look at here. First, what we need to do is we need to calculate how long we need to apply the reinforcement. You see, so we consider the block of retained soil. So how long it should be and how thick they should be. We already know the spacings, yeah, because vertical spacing 0.6, horizontal spacing 1. Good. Our job is to calculate L and then also thickness. Good. Let's calculate. Where is the equation? Can I go back now to check where is the equation that has T? Yeah, T here. You see? Can you copy this equation now at 0.39? Come on. Factor of safety braking. Factor of safety of braking equal to the WT of Y, WTFY divided by sigma A, right? Oh, we need that. Sigma A means lateral loss pressure. So Ka gamma heads, yeah, SV as heads. Do you understand? That's the sigma V A, right? Yeah. So what that means is active lateral loss pressure. Good. So now can we substitute the value in from our problem to get the value of T? That is our problem, that one. Come on, guys, let's do. The factor of safety, again, pull out is 3. A braking, right? Not pull out. It's a braking question. All right, because thickness we are calculating. 3 equal to, what is the width? W? Come on. Keep talking. 75 millimeter. So it is, we put in 1 unit. So it's better to have is the meter. Good. All right. So thickness we will be calculating because that's not provided. All right. Yeah. And then what is Fy? Fy value is given must be how much? 24. Oh, I think they missed something. There should be one more zeros. All right. Okay. Can we put that in? We'll check later on. All right. So there should be one more zero. Otherwise, you can't have comma between two. I think they mistyped that. So 24,000. Is this one more? Yeah, 240,000. So 4 zeros, right? Okay. I think they missed that there. I'll check later on. So divide by, what is Ka? Come on, guys. Can you calculate Ka now here? 1 minus sine, what is the backfill? 36, yeah? 36 divided by 1 plus sine 36. Rankine theory, yeah? Easy. Come on, give me the value for me.
So 0.259.
259. Okay, it's just right. 0.26 then. Is that right? Yeah, very, very easy. It does not matter, a little bit different. All right, 0.26. Okay, good. 0.26. times gamma of the backfill. Backfill material is 16.5. Can I check now? Yeah, 16.5 backfill, 16.5. So heads height, total height is what? Is it 10 meter? Oh, very long, 10. And then SV has heads, they must be given 0.6 and 1. 0.6 and 1. Can you solve for T now, please? How much would be the thickness? Thickness of the tie. How much you got? So 3 times 0.26.
0.075 into alpha x.
And so now it's this. Let me do that. Yeah, so 0.33 times 0.26. I just multiply the bottom all, right? Yeah, multiply by 16.5. Multiply by 10. Multiply by 0.6. Multiply by 1 does not change. That's the value we got at the top. So divided by 0.075 divided by what, 240,000, right? Yeah, 41, 2, 3. Is that's the meter, right? Yeah, of course. Thickness of the tie cannot be in meters. So let's multiply in 1,000.
4.29, yeah.
Yeah, it's 4.29, right? Okay. So that would be 4.29 millimeter. If you ask, go and buy manufacturer, can you give me 4.29 millimeter tie? They will hate you. So just go for the next whole number. Use what? 5 millimeter, all right? Nothing wrong. You can't come down, right? Yeah. Going up is always there. It's good, yeah? All right. So now what I said before, we need to calculate now how long this tie would be. That's the thickness of the tie now, length of the tie next. Can we do now? Yeah. Length would be, all right, yeah. So LR, which is the Feller line, plus LE, effective length. Okay, so but that is a straight equation given, so you don't need to even break down that. What is the length equation? Here you go. Did you see at the bottom? Yeah. All right, here you go, the equation, right? Yeah, so can I just show you now? Can we copy that equation now? Minus Z, total height minus vertical from the top, divided by 10. 45, how much is the phi, backfill phi? 36, right? Yeah. 36, half of 36 is 18, 18 plus 45, 63. Can I write this straight 63 here? 1063 plus FS pull out, yeah. Maybe can I write FS pull out, right? Yeah, FS factor of safety pull out times, that's the lateral loss pressure. So that must be Ka gamma heads, the top part, right? The granular field, and the SVS heads divided by, so 2W. That's the pressure on the, it's not and lateral, so just the gamma heads only because it's the vertical effective, right? Overburden pressure, and a 10 friction, right? Yeah, by U. All right. So let's go back and then have a look on these numbers, what they give us. There you go. Can we substitute these values now? H is 10. Minus Z, we don't know, right? Because Z is in different depths, length will be different, divided by 1063, good, plus I think that looks like these two are canceled each other, right? That two are same. Yeah. So that means our factor of safety pull out
3.
3. All right. 3 times K we just calculated, I believe. Oh, come on. Tell me what we calculated before.
0.26.
0.26.
Okay, thank you. All right. So SBSS, we already know that, right? So 0.6 and 1, 0.6 and 1 divided by 2. W is given, right? So 0.075. Yeah. And then times 10, 5 mu. I think 5 mu should be given. It's a 20-degree frictions, right? So 10, 20. Oh, interesting. Second part didn't depend on height. So it's easy now. All right.
So now we need to know for calculating Z, we need to know L. For calculating L, we need to know Z.
Yeah, so yeah, the Z is a different depth, right? Yeah, so did you see here in the diagram? Z is
Yeah.
from top different depth. So first you keep Z there, compute everything, and then for 0 meter, 2 meter, 4 meter, we need to calculate a different depth,
Okay.
right? Okay, that's good. So now 10 minus Z equal 10 minus Z divided by 1063 degree. Plus, can you compute this all? Because that looks constant, so it does not change anyway. So 3 times 0.26 times 0.6 divided by 2 divided by 0.075 divided by 20. What is 10? There, yeah, equal to 8.57, right? 8.57. So now let's compute different length first. So at Z equal to 0, what happens? L equal to, if that is 0, so 10 divided by that, right? Yeah. So when Z equal to 0 at the top. Okay. But top is usually we ignore, right? Okay. So that means 10 divided by, but let's calculate. 10 divided by 63. 10, right? Yeah, that's the one. Oh, what happens? 10 divided by 63, 10 equal to 5 plus 8.57, right? 8.57. So total is 13.66, 13.66. Good, right? Yeah. So Z equal to
13.7. It's mm, yes, sir.
no, it's a meter length, because it's the
Okay.
length of the tie. It should be very long to go inside the wall.
Okay.
It's all meter. I think we all converted into meter anyway. Yeah, it's a meter. So 2 meter now. L equal to 2 meter depth. What happens? That's the 8 divided by 63, 10 equal to that, plus again 8.57.
12.65, sir.
12.65, correct. 12.65. How long is 10 meter, right? Okay. Maybe I want to check, just go down at the bottom first, right? 10 meter. What happens L equal? 8.57, right? If
Yes.
it is 10, that means that's 0, isn't it, right? You see,
Yeah.
Rankine spacer it starts from the bottom of the wall. You see how easy that is, right? So that means there is no that part of the length, only the other part, LE is there. It's good. All right. So now, what do you think? So it is better to use 1, all right? So it means maybe L equal 13 meter would be enough, right?
Yeah.
Because little bit more there at the top, but really top, we don't provide the reinforcement at the top. We provide at least some distance down, isn't it? Yeah. You see, so that means if it is safe, that means just above 13 would be good. So L equal to 13 meter. You see now how easy we calculated both. So that would be from here to here. From here to here is how much is that? 13 meter, yeah. Because we try to provide all throughout. You already saw that, right? Actually, length at the top is highest, and it keeps going down the lowest at the bottom. It's good, right? But for you can do this way, right? Calculate few, and then at the bottom, at the middle, at the top, and then you get approximately. But it will be maximum at the top anyway. Good. So now we did the calculations for internal stability analysis, all right? So now next step is our to calculate the external stability. So whether it what goes away or not. Do you mind? I just remove this here and I do it over here because I don't want to redraw again this.
Yes,
Should
sir.
be fine, yeah, all right. Okay. So just I want to just remove that because I already calculated this. So let's do 3 checking now. Number 1 is sliding, whether this wall will slide or not. Okay, external checking, so which is sliding. To slide, because you see earth pressure. Can I draw the earth pressure diagram now? We already know, yeah, how to calculate that. How much was there? Ka, yeah, gamma h, right, at the bottom. So Ka was 0.26, gamma is 16.5, h is 10. Can you calculate for me that, please?
$42.9.
Okay, 2.9. We'll check later on. All right, kilonewton per meter square. How much is the total pressure now? Yeah, that's the total force. Calculate the area of this triangle.
Yeah.
That's what we did since long, so many times already. Yeah.
214.5.
114.5 kilonewton. It's a load now, right? It's kilonewton, right? Force. So now, what is the vertical now? Vertical total weight of this block, all of it, W. And what is the area? 13 times height is 10. And what's the density? Density of soil, we can use the same because reinforcement, keeping reinforcement will not change that much because we just provide few strips around, isn't it? Yeah. So can I do 16.5 now? How much total weight pulling down?
Yeah. Ten 16.5.
Sorry, say again one more time, please.
2145, sir.
2145 kilonewton, yeah?
Yeah.
All right, so in sliding means there is a friction. Because of that, I think pi mu was 20 degree we used before. Yeah, I remember that now. So that load times that's the resisting because it goes this way and that's pulling out. So now factor of safety sliding equal to what is resistance is that one 2145 2145. All right, and multiply by what 10 20. Yeah, that's the friction force divided by pushing out force 214.5. Come on, how much you get? Calculate that. Yeah.
3.64, sir.
Oh, is that good or not good? It's good, yeah. 3 factor of safety 3 is good enough, right? Yeah. 3 point. How much you said?
6.4.
6. All right. Another is again factor of safety for what? Overturning. So this force will overturn, right? Yeah, and that force will resist, isn't it? Right. So resist force is W 2145 2145 times it will act what at the center here. From here there is 6.5.
Yeah, 6.5.
Yeah, divided by this will overturn. So 214.5 times where it acts 1/3 of the
10 by 3.
10/3. Oh, it should be even. Good. It will not overturn. Yeah, that's a 13-meter long wall. Come on, hey, there is no way. How much you got? Oh, one thing we forgot, eh? Yeah, just the previous one. It's not 10. I think we said 2/3. We need to take that angle, right? Can I check already? That was I think we need to take 2/3. Sorry, guys. Yeah, did you see that here? K5, we just did 10, 5 only, right? 5 was 20. You see? So it's a 2/3. We got to do that. All right. Sorry, that must be 2/3 of this angle, right? Can you redo again, please? That calculation, particular one. We need to do 2/3 of the angle, not the full angle there. Yeah.
One, five.
2/3 of the angle, but I think this is 5/1, and I can check again, not 20. Because we are doing sliding, isn't it, right? Yeah. So that is not what we needed to do. So 2/3 of that angle is. Can I go back one more time? Because we missed this little bit concept there. 5/1 is at the top, yeah? Can I check now here? So 5/1, just a moment. 5/1 at the backfield, so not the 20 again. This should be 36. Please. Oh, that would be more or less similar. So 2/3 of 36 is what? 24, isn't it? Yeah, total is 24. All right. Can you check now one more time? So that's there. 2/3, we must do that, yeah. So because 21, 45 times 2410. Yeah. So divided by 214.5. So 4.45. Yeah, even better. So that's okay. So we were on the safe side, by the way. So 4.45. That's okay. But that's what they suggested. So it's better to use that. Okay, 2/3 of that backfill friction angle. How much you got overturning?
It's like greater than 19, 19.5.
Yeah, okay, let's write 20 then. You see how big that is. Okay. Of course, this is 13-meter long wall. Will not overturn for sure. Yeah. So that makes sense. So now we need the bearing capacity now, the third one. So hopefully we know that, right? So can I just do this bearing capacity one? The factor of safety bearing capacity. We need to use some theory now. So it's the foundation now we are talking about, right? So what is the Q ultimate? CNC. We don't use correction factors, okay? So CNC plus, what was the other one? Second part. Gamma G NQ, yeah, plus half B gamma and gamma. If I remember correctly, that's the bearing capacity equation, right? Yeah.
Yes,
So,
sir.
yeah. So now this will be 0. Why? There is no depth, right?
Yeah.
You see over here, no depth. So that's it. Let's put that one others. So C, what is the phi? 28. Can you check any methods you can use? Which one is maybe just use, let's say Vishik. Vishik equation. So what will be NQ and N gamma? So now I'll write here, right? Yeah, NQ. Oh, NQ we don't need. Yeah, only NC
And gamma.
and gamma. All right. So you need to check the foundation swirl, right? Which is 28 degree. All right. So let's go back to our lecture note long time ago. You can specify any method, all right? Not only basic, any other methods we can use. For now, just let's do basic. What is basic table? Hansen bearing capacity, that one, all right? Can you give me? basic what degree? 28. Oh, thanks God, 28 is there. Otherwise, interpolation is a little bit tricky. It's 28. So let's use NC is what? 25.79, right? 25.79. And then N gamma basic, right? Let's use that one 16.7. You need to specify, right? You need to specify the methods, otherwise the value will be different. Okay. So now can we do C? How much C there? 50. How much is NC? 25.79, 25.79 plus second term is 0, half. What is the width of footing? How long is that? 13. So gamma of the foundation, 17.3. And the N gamma is 16.3. Can I write that? 16.7. Can you compute this for me, please? Oh, too many writing here. So I want to delete that so that you don't confuse this. All right. Okay. There you go. How much is that? Ultimate bearing capacity at the foundation.
Three one six 3167.41.
21.
3167, sir.
3167 kilonewton per meter.
41.
That's all right point. Okay. I'm not doing that point things here. That's it. We got the pressure. What will be the given pressure here? This is the vertical pressure at this time, right? So that means factor of safety must be equal to, this is the ultimate pressure. So 63167 divided by given pressure is gamma D. That's it. How much you got? 16.5 times, what's the height? 10 meter, right? That's the pressure. You can directly calculate just the pressure given by overburden pressure at this point. That should be enough for this type of wall design. All right. Okay. So can you compute that? How much you get?
19.2.
Again, that big?
Yes, sir.
All right. 19.2. You see, that is too big. That's too big. That's also safe. If we design this type of reinforced wall, this should be safe enough. How you feel? Easy, yeah? Exactly same thing what we learned before, right? Overturning, sliding, and bearing capacity.
Yes, sir.
Only thing is you need to know how to calculate length and thickness of the tie. That's it. Yeah, it's quite simple. All right. So let's check whether our calculations are right or not here. I think it should be okay. Oh, that's a solution here, by the way. How much we got? Is this the length of tie we got? The thickness of the tie? Is that correct?
Yes, sir.
Okay. Oh, there was corrosion given, yeah? Yeah, we didn't read that bottom, okay? If corrosion given, so you need to increase by per year, that means it's 50, multiply that, add to that. You see, did you see that? That plus 50 years corrosion and the total this. So we need to use 6 millimeter thickness of the tie. Length calculation, same equation we use. Yeah. If you see here, you see a different depth, different length, right? Yeah. At the bottom is the shortest one. At the top, oh, they didn't even do 0, right? Is that so? They use the 13 meter. I think that's what we also use, right? Approximately.
Yes, sir. Yeah.
Good. Now, after that, then sliding, right? So let's start. So weight, we consider that. Overturning, can you check around 20?
Yes, sir.
Sliding around 4.5, around, yeah. That's 230. You see, that's the thing we need to be careful there. 2/3 of 36. Good. We use basic equation. 165 around 19.2. That's what we got for bearing capacity, yeah.
Yes, sir. Same.
You see, that easy, really. All right. Okay. So discard that. Now, I'm sure you will be able to design this wall. It's very simple, looks complicated by looking, but when you actually you do, look at these guys. I don't know why they needed to do this all, right? That is a very simple equation, just substitute back and get this answer, yeah? All good. So that's the first case. Second type of reinforcement we use is we call it geotextile. Can I go through the theory now, right? Yeah, geotextile. So there is no horizontal spacing for geotextile. It's a what? It's just the vertical spacing. Why no horizontal spacing? Because it's like a carpet, right? We put throughout the other side. Okay, so if I see from that side, all the way through, we put this geotextile. And also there is a little bit wrap length. Yeah. So for the geotextile, we need to calculate that. We call it LL. There are equations. LR and LE, same as what we did before. Is it simple? Same way. Only thing is you need to calculate SV here. All right. Over there is SV and SS. Let's go through that. There are steps here. Very easy. All right. Look at here. Step 1. Determine the active pressure. Of course, you know how to calculate active pressure on the wall, isn't it? Yeah. Rankin's pressure. Usually use the Rankin's theory. So now calculate allowable pull, right? Allowable tensile strength for the textile. So this is the formula in general, but it depends on ultimate divided by some of the reduction factors for different type of what they call damage or installation damage, creep, or biological degradation, so on, whatever is given. Just use that in step 2. But there are a lot of values here, by the way. And step 3, you calculate vertical spacing. Step 4, you calculate length. You remember that length? Same equations we used before. Yeah, exactly that. And then you just check the external stability. Again, what? Overturning, sliding, and a bearing capacity. Same process, yeah, just the some different formulas. Okay, let's do this example now. Oh, I have a lot. I just don't wanna discard that. So delete that part first, and then let's try to do this problem. All right, not this one. That one. Let's solve. I have steps, so I'll go to see the steps, right? Okay. So 5-meter wall, that wall is already drawn here, so I'm not going to draw. Is okay? Yeah. All right. Yeah. So now 5-meter wall, ultimate T is there, and then you need to calculate SV length and then lap length, right? Yeah. Also need to check the external internal stability. All right, here you go. So now what I need to do is I need to calculate SB, right? Yeah. Can I calculate SB? SB equal to, what is the formula for SB? That one. Can you copy that, guys? The second, the last one. So T allowable strength of tie, right? Gamma 1 ZKA, gamma 1 ZKA, and then factor of safety, factor of safety for breaking, tie breaking. Geotextile breaking here, all right? Not the tie. Oh, sorry, guys, yeah. There you go. So allowable would be, so T allowable would be T ultimate divided by whatever correction reduction factor are given, right? All of them, some of them, all of them. Can you calculate that now? What factors given in the question? T ultimate. How much is the ultimate strength? Can you read on the question? T ultimate is 52.5, yeah?
Okay.
Divided by whatever is reduction factor given, just use all of them. All right. So that means ID as a creep, and then there's a biological degree. So this is CB. Okay. The 3 of them, right? So 1.2 times 2.5 times 1.25. This is just to reducing some of the factors, right? Yeah. How much is that? Can you calculate the allowable mass? Allowable tension, right? Strength of the textile.
10.6, sir.
10.6. All right. Okay. So now, so we substitute in the equations to calculate SB, please. Yeah. So 10.6 kilonewton per meter. All right. Okay. So now, because the Z it varies, right? Spacing varies. You see, there is a Z there, isn't it? Right? Yeah. Starting at the top, how high is well? 5 meter, right? Can you take at least like 3 of them? One in the center, one at the top, and one at the bottom. Right? Yeah. At the top, Z is what? 0. So we can't calculate, right? At the top, really, isn't it? Right? So a little bit down first. Start now. So can I calculate now Z equal to, let's say, 2 meter, 2 meter depth? SP equal to what? 10.6 divided by what? Gamma of the backfill is how much is that?
So I got here allowable 14 kilonewton per meter.
Is it? So
Yeah.
2.5, 1.2, and then 1.25. It's a 52.5 is total, right? Is that all right? Can I check now? Yeah. Okay, thanks. Thanks for that. So what is here is 14. Yeah, that may be better. So 52.5 divided by 1.2 divided by 2.5 divided by 1.25. It's a 14, exactly. Make sense? Yeah, all right. Just a competition calculator use.
It's the sum or multiplication, sir. Like you say, like sum of reduction factor, summation of.
No, summation means all of them here. Oh, I think I made a little bit mistake here. All right. So this is not like a 1 plus another plus another. So all of those in multiply. So what that means is included. So I shouldn't write that. And I check now. We need to go here, right, guys? Yeah, always. That's it, right? Did you see here at the bottom is a multiply? Did you see that 8.56 equation? Yeah. Ultimate divide by whatever factors, whatever given, all of them there. And there's a multiply, not the sum. You are right. Okay, that may be the confusion. All right. Is it clear now? Yeah. So 14 divided by gamma. Gamma is how much was the backfill unit weight?
15.7.
15.7. Good. 15.7. Now for Z, I just use 2 for now. Yeah. And the K, oh, we haven't calculated 36. I think that's the same, right? Before also we had 36, yeah. Previous problem we did also. So that must be K, must be there. How much is that now? Yeah, Ka.
0.26, same.
0.26, right?
Yeah.
Yeah. Oh, that's lovely. Easy. So 0.26. And then FB. Is this given? Factor of safety for brake type, the geotextile breakage? FB, where is that?
No, sir.
Then we need to see what they recommend to use. All right. Otherwise, we can't calculate those all, right? We need to check. If not given, I think we need to check for that. Let's go back and have a look what they recommend. What is the factor of safety, right? Breakage, right? Yeah. FB. So what they say, magnitude of FB is generally 1.3 to 1.5. Let's use 1.5 to be on the safe side. Yeah. Good. So can you calculate SB at 2 meter depth first? How much you got? Vertical spacing. Fourteen divided by 15.7 divided by 2 divided by 0.26 divided by 1.5. 1.14, yeah? That's quite huge, right? Let's do the calculation at the end. High meter wall, yeah? SB equal to 14. Oh, that would be the minimum based on the equation, right? Yeah, 15.7 times that should be 5. So 0.26 times 1.5. Come on, can you give me the calculations for this? What divided by 15 point and by 5 by 0.6 by 1.5. 0.45.
Yes, sir.
You see at the top around, you get around 1 point something. That's a to be safe side. Just let's use 0.5. Just be equal to 0.5. Spacing every half a meter. Yeah, we put the vertically the geotextile in vertical layers. It's good, yeah. That's all right. So now we need to calculate length, right? Yeah. So length L equal to. Can I just copy those? L equal to H minus Z, the same formula. Hey, we did that. Then I think 63. That's a 36. Yeah. So same 63 plus other side is SB. L is SB times what is that? Sigma is the lateral of pressure. So Ka gamma H. Yeah. And then factor of safety pull out. Factor of safety pull out divided by 2 sigma naught. 2 sigma is gamma H again. Yeah. And then 10 pi F times 10 pi F here, right? Not the other one. Okay, good. 10. How much was the bottom given? Pi F is given. Nothing there, yeah. Without and anything given, design of that one's also. So we do what we write there. So pi F must be 2/3 of that again, right? So 2/3 of that. So if not given, so we need to use that one. Okay, so now 2/3 of 36, right? 2/3 of 36 degree. Good. So equal to H minus Z divided by 1063 plus how much SB we calculated? 0.5 just before, yeah. K is 0.26. Can I just cancel these two? And then how much factor of safety pull out? Is that given? No factor of safety given, right? So go back and check now. So a factor of safety pull out is 1.32, 1.5 again here. Yeah. So can I write 1.5 for this also? 1.5 divided by 2 times 10, 24. Is good? So now, can you compute now? So H minus Z over 1063 plus how much will be that part? 0.5 times 0.26 times 1.5 divided by 2 divided by 2410. Oh, that's a very small, the other side, yeah? How much is that? 0.22. 0.22. So because when Z equal to 0, we get the highest value, isn't it, right? Can I just check that, right? So Z equal to 0 at the top. So that means 5 divided by 1063 degree plus 0.22. How much will be this? 5 divided by 63, 10
7.1.
plus 0.22. That's the maximum, 2.75, right? Yeah, 2.75, 76 meter. That's the maximum, but we don't need it at the top, right? That's the maximum we have. So maybe that's too much. Just use 2.5 then. Length equal 2.5 meter, because that's the maximum at the top. Yeah. But if you go down, you remember that will be very long, and then slowly goes down like that, isn't it? Yeah. So in this case, it's instead of providing like this, just use 2.5 meter throughout. So it will be safe. It's good, right? So we got L equal to 2.5 meter. Who can tell me what I need to do now? So I already know the wall, right? Yeah. So there is a, oh, that's the wrapping length like this. That's the length. I don't know how I draw this. Okay. The geotextile thing. Yeah. So from here to here is 2.5 meter. The wall is how long? How high is this? 5 meter wall, right? So that's it. So we need to get this length. Okay, wrapping length. How much is that? So there is a formula for that. This one. Can I enlarge a little bit? Can you copy that formula? You see this one. Step 5. So LL equal to SB 0.5 or sigma Ka. We have that, right? So it's a 0.26. Already we had. Factor of safety pull out 1.5 divided by 4 times, that's what I need is gamma D gone, right? Yeah, 10. I think that's 24 degree we used before. Yeah, IF, yeah. Come on, how much? Can you calculate that? 0.5 times 0.26 times 1.5 equal to divided by 4 divided by 2410. 0.11, right? Look at this, 0.11 meter, but we need to, at least we need 1 meter minimum. So that means you just provide that from here to here is 1 meter. So we did the internal stability, yeah. Need to check external stability. You already know, right? I'm not going to do all, right? Let's do sliding. Factor of safety, sliding. What prevents sliding? Over there, the friction there in the base of the wall. What wishes for sliding is PA. PA equal to what? Oh, you need to draw this pressure diagram, right? Yeah, that's the pressure diagram. How much is the bottom one now? 0.26 times 5 times what? Gamma D, right? Gamma of the soil is, how much was that there? Backfill material, 15.7. Could you please calculate that for me?
20.41.
20.41, right? Kilonewton per meter square. That's the pressure. So you need to get the total now. Calculate the area of this triangle to get the total PA.
It's 51.025.
Say again, please. Yeah,
51.025.
51.
Yeah.
Okay, just right, 51 for now. All right, okay. So that's the disturbing. It should be at the bottom. And then the resisting is that total. How much is the weight now? 2.5 times 5, yeah. So W that. So that means 2.5 times 5 times what's the 15.7? That's the total. 196.25. Did you get that? Weight of this block. Is that okay?
Yeah.
Okay. So 196.25, 196.25, but there is a, because of this friction, 2/3 of that again, 196.25 times 10, 2/3 of 36. Can you calculate now what's the factor of safety you got? One 96 point.
It's 1.71.
Times 2410. That's divided by 51. Oh, look at this, 1.71, yeah? You see, this is a little bit tricky here. What can be the reason? Can anybody tell me why we got this really low factor of safety here? Because length of the block is small, right? 2.5. Previously, we had what? 13 meter long, yeah? That's why it was more stable. So I would recommend not 2.5 now, maybe go 3. Yeah, 3 meter, right? So that it will be a little bit more safer. All right, overturning now, factor of safety overturning. This W will resist, right? It will be at the bottom. And no, resist at the top, right? Yeah, so that will be 51 times what? 5/3. That will be the, what I'm doing. Always resisting at the top, isn't it, right? So that means 196.25 times where it X. Half of that, right? Half of that is 1.75, is that? Oh, no. 1.25. Divided by, so this will try to overturn. So 51 times, the length is 5/3. Can you calculate overturning?
It's 2.9, sir.
Or 2.9. Okay, that's okay. It's not that bad, yeah. But they are all critical. So I would, if I am a designer, I'll go a little bit more length there. All right, bearing capacity now. Again, the same process, right? Yeah, factor of safety for bearing capacity equal to ultimate. So now ultimate bearing capacity. So C and C, is there any bottom value given? Okay, there are. So C and C, right? C is 28. I don't know NC. What is the degree? 22 degrees, right? What will be NC now? 22.
There's no 22.
This kills me now, easy. Did you see that? Yeah. Oh, do I have the what I call Terzaghi one table? Is it 22 there? Nah.
No, sir.
Oh, okay, come on. Now we need to use this equation. All right. Can I just, for now, of course, guys, you know how to calculate, right? NC, you find NQ from that equation, right? And then you find NC there and N gamma there, or if you want to use mirror. There are other equations also given, right? These all. Oh, come on, that would be tough. So I just guess now. Interpolation. So NC would be interesting. So NC would be, so 22, right? Yeah, 22 means almost halfway in middle of that. How much I can use now? So a little bit towards 20. So it must be around 16, yeah? 16.5. Let's write that 16.5 for now. Yeah, CNC plus half. Okay, the third term now. Plus half B. B is 2.5. All right, yeah. Yeah, B is 2.5. Maybe it will be a little bit 17 side, but does not matter really. So 2.5, and then B is done, half B. Gamma, how much is the gamma? Base of the soil gamma. 18. Yeah, gamma and gamma. So can I check the same table now? And gamma, right? Yeah, so 22 here, somewhere here. Which location? Just use the basic, yeah. Again, yeah. The basic equation would be around, how much do you think is the good one? Around 7? Yeah, 5 to 10, right? Yeah, in between, so it's around 7. All good. So that's the ultimate divided by pressure at the bottom. Pressure at the bottom is 5 meter high with that gamma. So that means 5 times what's the gamma? Gamma of the backfill now. 15.7. Could you please calculate what you get the factor of safety for the carrying capacity? I think it should be good enough, right? 2.5 meter wide, yeah. So bearing foundation shouldn't be that huge issue because we have just 5 meter height wall. Come on,
It's 7.89.
7.89 or around 8, right? Okay, can I just find that around 8? Yeah, but you need to do the correct calculations once you use the formula. All right, let's check. Oh, this is the one, yeah. So this is the second problem. So I deleted that. I'm not sure whether they come back or not. Oh, now I'm in trouble. I should just not save that, yeah. Hopefully it didn't disturb my calculations, my lecture note, hopefully. What's that? We did what? Geotextile, yeah, this one. What is that? It's good, yeah. So we got allowable 14. That's okay, yeah. So we got different for SB. So we use how much we use the SB? I think we use the 0.5. That's okay, yeah. Approximately that value. Length we calculated. So length total is around 2.5 we use. That's good, yeah. So lap length is very small. So that means we use 1 meter, right? That's the minimum required. Oh, that was okay. And let's talk about overturning. How much we got overturning? Is that all right?
Yes, sir. 2.9. Yeah.
All right. Okay, that's fine. So we use this block anyway, so we should be all right. And the sliding, yeah, 2/3 again. Don't forget that. Okay, all the time. Is it about
Yes, sir. Same.
1.7?
Yeah.
Okay, but little bit be careful here, right? Yeah, that's fine. And so that's the same equation we use, right, for bearing capacity. So around 8. Yeah, that makes sense. You got it now, yeah. Same thing, repeats again and again. How you feel? Easy, yeah? No? So there are formulas, right? Just need to learn, right? That's 6 steps, right? Lateral loss pressure, type of reinforcement, spacing and detailing, length, yeah. And then we do the what we call that one is, yeah, we just check those 3 things: sliding, overturning, and bearing capacity. Okay, so I think enough for today. So now let's go quickly through the lectures, right? Yeah. GeoGrid again, same process. Did you see that? GeoGrid, the third type of reinforcement we use, right? Yeah. So step 1, you calculate earth pressure. We know that how to calculate. Step 2, you calculate allowable. Again, the same similar formula. You can use that depending upon what values are given. Step 3, calculate vertical spacing. And there are some factors. You see, you just take from the either table or there should be given somewhere. And then calculate length. That's what exactly we use, right? For all types. And then total length. Good, right? So be careful, the CR and the CI are given. So at least you can take out from the table. And external stability, what? You do overturning, sliding, and a bearing capacity again. Same repetition for the same process. So this is a very good book. That's why I try to refer to this book. Okay, so it's a clearly written stepwise process, all formulas there, and so on. Let's do this now. I'm not going to do it here, but just check. First thing is what? Design wall, determine SB and L. Only two things, right? We don't need to check external and internal stability. Can we do that now, just now? All right, can I just enlarge this? Just a question only, all right? So we need to calculate SB. What is the formula for SB? This one. Can you copy that now? Another tutorial problem. So step 3 now, yeah? Step 3 has to be equal to T allowable and a CR divided by, that's the lateral of pressure, right? So Ka gamma head FSB. That's it. All right, equal to allowable. So I want to check whether allowable given or from we need to calculate from ultimate. T allowable given, no. T allowable given directly. Did you see that here? Can I just enlarge that? Just that part, question part only. Did you see T allowable given 45? You can directly write that. Times, what is CR? 0.8. Ka, oh, what is the phi? 35. Can you calculate Ka now? So 1 minus sine 35 divided by 1 plus sine 35. Can you calculate this for me, please, for Ka? Because that's the angle is different than before, so I need to calculate. Come on, be active, not lazy.
1.027, yeah.
0.27, right? It's just a little bit off. Yeah, that's all right. Okay. 0.27 times. And then now what is gamma? Is how high is the wall?
Gamma is 16.
16.5. 16.5, right? Yeah. How high is the wall?
6 meter, yeah.
6 meter. All right. Okay, 6 meter. Factor of safety for breakage, right? Yeah. Yeah. B 1.5. Yeah. Did you see that there? 1.5. That's it. That's the vertical spacing. But again, right? Again, because H is we calculated at the bottom, yeah? At the top would be very big. So bottom would be enough to give us the idea. Come on, how much is it? So bottom would be the most critical anyway. So 45 times 0.8 divided by 0.27 divided by 16.5 divided by 6 divided by 1.5. Is that what we got at the bottom? So,
Yes, so yeah.
so 0.89, right? Yeah, but this is too low at the bottom, right? At the bottom of that. So above this will be bigger spacing. So that's what they suggested. I think they calculated only 5. Did you see here? Yeah, they didn't go down to 6. So then approximately around 1 meter was enough vertical spacing. So every 1 meter spacing vertically, the geogrid was put there. All right. So maybe I'll just see 1 meter is enough for there. What we need? Length now. Same thing. Length formula here. Maybe I'll not do it here because solution here, right? Yeah. So all formula you can put that in. So Z varies. Can you tell me where will be the critical length, maximum length, where we get? At the top, right? When z equal to 0, isn't it, right? Yeah, so you can use that directly and then check if you want. Good, right? And they use 3 meter. So again, length is what? Always LR plus LE. You see, that's the equation used. That's a LR, that's a LR, that's a LE. Just substitute sub in, and then you get a different depths, different values, but at the top is the highest. So why not just use around 3.5 meter? What is left now? So you need to check external stability, sliding, and then what we call sliding, overturning, and bearing capacity. Okay, but in this problem, it is not asked. So don't worry about that. I think they asked only for what? Vertical spacing and length. How easy this is, right? It's the same process for all 3 types of reinforcement wall design. Okay, so only thing is metal strips. You need to calculate horizontal and vertical spacing, not only vertical, for geotextile and geogrids. We need to calculate both designs. I think in your some of you guys chose the soil stabilization project and things. I thought you would go a little bit in detail in like a design and showing some example design of the wall, those type of things. But you mostly focused on maybe just the soil improvement type things, not the retaining walls design. Yeah. All right. That's it for today, guys. Yeah. So you can solve all tutorial problems, just these concepts. That's the reason why I put these all problems here, so that you have all examples, 3 types. Okay, example, 3 examples. It will be so easy after knowing this to solve any problems. That's why I copied from the book and then put here, so that everything is clear for you. So in the class test, yeah, so we will getting similar this type of problems. So you need to solve them. And then probably we will be going for the class test, the online, yeah, if you want to do that. Any questions for me?
No, sir.
No? All right. Okay, thanks. I think sorry for Monday because I couldn't cover. Hopefully, I'm still testing positive until now. Hopefully I'll be fully recovered by Friday. Yeah. I couldn't mute. Hey, yeah. Sanjeev, could you mute? It's coming noise and then can't talk. All right. Yeah. Okay. So what's happening? Who is? I don't understand. I couldn't turn off the muting and then not sure. Could you please turn off your microphone? It should work when I mute. Okay, that's all right. Okay, thanks guys. Yeah. Again, turn on. You guys also hear the noise, yeah?
Yes, sir.
Yes, sir.
Could you please mute your microphone when you're not talking? If asking questions is good. Yeah, is all right? Okay. I need to remove now. Quiet sometimes, and then later on it starts coming again, the noise. Anyway, okay, thanks. We finished week 7. Yeah, I couldn't come on Monday, but hopefully next Monday I will be there. Yeah, So please, we will be doing all of the sessions your lab. Okay, so your what we call the GeoStudio lab, because this software thing is killing us. So we need to finish your assignment too. Okay, so we'll be doing all Monday for this software thing, right? For your assignment too. And then hopefully that should be good enough. All right. It's okay. Yeah.
Yes, sir.
Okay. So please do come on Monday. If you miss and then yeah, I can't follow those type of things, can you bring that assignment also with you? Okay. Assignment 2, so that we'll be doing over there. So we'll not talk new theory anymore. So we will be doing that, let's say 4 hours. Just use that and try to finish as quickly as possible. Bye for now, guys. Yeah. See ya.
Thank you, sir.
Thank you, sir.
Bye.
Thank you, sir.